Hello, everyone. Maybe you're like me. You've spent some time looking around. There's all these latest and greatest announcements, as well as 3D printers that have been released that are just super, super fast, like this one over here. And if you're like me and you've been using your 3D printer for the last couple of years, maybe 2 to 5 years, and you're starting to think about the fact that yours is kind of slow, like mine, um, well, maybe this video can help. And so I've spent some time thinking about things, and I've decided I want to try and improve my current 3D printer. I happen to have a Voron 2.4. It used to be fast, or at least what used to be considered fast, but it's become a little bit of a slouch now compared to everything else out there. Everything I'm about to show you will apply to pretty much any other printer out there, whether you built it or whether you purchased it, as long as you're possibly interested in going in and making some changes. But anyway, here we go. So I decided to set some goals. I wanted to hit 50,000 acceleration with a minimum of 600 millimeters per second speed, no speeds below 400 millimeters per second. And I wanted my acceleration, although to hit 50, I wasn't interested in anything below 35, and I really wasn't interested in anything over 100K. And then most importantly, whatever or however I was going to modify, and knowing I had to modify the motors and voltage here, I was going to target or at least decide not to add any additional cooling for the motors. So you can test this out without using new motors, but I decided to purchase some new motors. And so here I have these Kraken V1 zero point 0.9 degree stepper motors. I know most of you will be wondering why 0.9, but my printer, at least traditionally, since I've built it, has had 400 steps per rotation, and I wanted to stick with that. And so here I'm opening up the package. As you can see, it's size. It's very much different in terms of size and height. The shaft is also longer as well. It does come with a new pulley. I believe this is a 30-tooth pulley, but at least for now, I'm not going to use this. I'm going to stick with the standard 20-tooth pulley. And it comes with the wires pre-terminated. You may notice an extra set of wires here, the white ones, because these motors, you can read the temperature, internal temperature of the motors in Clipper using your fluid or mainsail interface. And at least for me, I thought this was going to be really important, especially in those early days when I'm testing these on long prints. I want to make sure that the motors don't get hot enough to melt my printer apart because, as many of you Voron owners know, parts of your printer are definitely 3D printed. And by the way, again, you don't have to purchase new motors. You can run the tests that I'm about to run on higher voltage with your existing motors. And in fact, you may want to do that before deciding to go out and purchase additional motors. If your MCU doesn't support high voltage, anything beyond 12 or 24 volts, you're going to have to change it. And this is where it might get a little bit tricky because if you've never done that before, uh, it's something you'll have to get over. But here you see I have both my 24 volt and my 60 volt power supply, as well as my Kraken MCU. And my pre-existing one, which was an old Spider V1, did not support the higher voltages. This one has a series of 5160 drivers, or at least repackaged 5160 drivers, and they handle the high voltage up to 60 volts. Here you can see the input for the 60 volts for the motors. There is also input for standard 24 voltage to power the board. I've added a cooling fan because these will generate considerable heat. There's a really nice set of cooling fans here. And also I've moved the backside cooling fans, which is what I was trying to point to help blow some of the air away from here as well too, the heat. Um, I There are 4 drivers. This can drive a total of 8. 4 for a total of 8 amps, and then 3 for 3 amps each. And so my Z motors are connected to the smaller current handling side of this, and my AB drives are connected to the higher current handling as well. It's hard to see here, but there's actually a CAN bus cable going into here, and the CAN bus is running off the 24-volt power supply, which is being powered through the card, and my tool head is operating still off of 24 volts. And here I've got the bed. My bed is hooked up to AC main, but if you have a standard bed heater, it would be 24 volts. And here you see two additional inputs for measuring temperature that I have connected, although I have the motors connected elsewhere on their card, and well, that's another story. I highly recommend you get one of these temperature probes. In my case, I'll be reading the temperatures from the motors, but it's still really important to check the outside of the motor because we're ramping up the power, I'm ramping up the amperage, and I want to know long term that the motors don't get so hot that they melt parts of this printer. To run the actual tests, I went to Ellis's print tuning guide. And one of the sections here is about testing your maximum acceleration and print speed for your printer. And here's a little comment. If you use 0.9 steppers like I'm doing, you'll hit lower speeds. In addition, there's some commentary here about adjusting the amperage to make your printer go faster. But in this case, I'm actually adjusting voltage, which will increase the speed as well. And you'll have to download and install this macro, which is super easy to do. You can just download the file, load it into Clipper using Mainsail or Fluid, and just include it in your standard file. And if you go through here, there's instructions here on how to test the speed as well as the acceleration. And this is simply what I followed. Here's what the test looks like. It does a home, and then after a home, it proceeds with the actual test. You'll run this over and over and over again with higher and higher accelerations and higher speeds until the test stalls. And once you think you've found the maximum what your printer can do, you can run it 10 or 20 times in a row. The script allows you to do that. One other thing to keep in mind, when you up the voltage on your printer, if you have homing that doesn't use end stops, you'll probably have to adjust it when you first bump it up to the next higher voltage. But I found it actually easier to do at the higher voltages, so it was quick and easy. I also strongly recommend that you run Clipper's Auto Tune. This is something that you'll need to install. I found after installing this, my 3D printer was able to run faster and hit higher accelerations. Here it shows you the drivers that it supports. It's fairly simple installation. You'll have to do this at the command line of your Pi. And then in addition here, here's some changes to make sure automatic updates occur. There's some couple of simple changes to your existing configuration. It speaks a little bit about sensorless homing if you have it. I do. It really wasn't an issue. And then you'll have to add this auto tune section as well. And then if you like, there's some parameters that you can set here. I left all of them alone except for one. One of them is this tuning goal, and it defaults to performance for your AB or XY motors and silent for your Z. In my case, after letting it run this way, the Z drives were really noisy for some odd reason, although they worked really well. But I decided to switch it to performance as well, and it turned out my Z drives got quieter. Again, that's probably a little bit of a quirk with just my installation. I really doubt that most other people will encounter it. So now let's see the test results. So I ran the tests at 24, 36, 48, and 60 volts. And taking a look at this chart here, well, the voltage across the bottom or the bars, and then on the left-hand side are the accelerations. And at 24 volts, I actually hit 35,000 millimeters per second square, which is great. At 36 volts, I hit 40, which was a little bit surprising. I was expecting a bigger jump than that from 36 volts. At 48 volts, I hit 85,000 millimeters per second squared for acceleration, which is actually a huge jump from 36. It's massive, actually. Um, in addition, at 60 volts, I was actually able to hit 100,000 millimeters per second squared acceleration, which is massive over the original 35,000. In total, represents the biggest jump. When I look at voltage versus speed, here we can see at 24 volts, I was able to hit 400 millimeters per second. 36 volt, 500 millimeters per second. Again, not quite the jump I was hoping for at 36, but at 48, I was able to hit 600. And at 60 volts, which represents the greatest jump overall, I was able to hit 1,000 millimeters per second. But you'll see later on that was at a vastly lower acceleration, at least one that I was planning on. Taking a look at this, I've plotted out 24, 36, 48, and 60 volts. Here you can see the 35,000 at 400, I got at 24. At 36, I didn't get all that much. It was really 500 at up to 40. But then looking at 48 volts, I got up to 600 millimeters per second at just under my target of 50. This happened at 45,000 millimeters per second acceleration, and then gradually drops down and then levels out at an acceleration of 70,000, where it kind of sits at 450 millimeters per second. If you take a look at 60 volts, I was able to hit 1,000 millimeters per second at 25,000 acceleration. It drops rather quickly until we hit 35,000 acceleration, where it levels out for a little bit. And then we see another drop from 45 to 50 or 55, where it's sitting at about 600, which is the actual speed I was looking for. This empty spot here, I decided to skip because it seemed way back at 55 I wasn't going to be making a lot of progress. And so I jumped all the way up to 80K, where I was still able to hit 600 millimeters per second. But then we see a little drop again down to 550, where after 95 it tapers off some more. Now, I wanted to understand, this is what I should have done first before doing my test, but I did backwards. If I have an average print size of 150 millimeters, if I need to travel or lay down plastic at 150 millimeters, um, what acceleration and what does acceleration and speed, how does that impact this? And if you look at 1,000 acceleration, I get nowhere. I can't hit even 400. At 2,000, I'm doing pretty good at 400, and I can even make a decent amount of distance here with 500 millimeters per second speed. But at 5,000, we see a huge increase. And it's across the board. I can actually hit for a short period of time 800 millimeters per second on that 150 millimeter track. Now, when I get to 10,000, we're in serious territory here. I can almost cover the full 150 millimeters at 400. I can cover 125 at 500. And the reality here is at all of these speeds, with 10,000 acceleration, more than half of that 150 millimeters is being spent at that speed, which is where I want it to be. I see another jump at 20,000, but it's nowhere near as impressive as the jump to 10,000. And at 30,000, yeah, it gets a little bit better. Although really I mainly see it at the 800, maybe even the 700 speeds. And then from 40,000 on, I'm not sure I'm seeing a lot that's worth it, which is interesting because if you remember, I chose 50K, and if I would have looked at this first, I don't think I would have chosen it. I probably would have chosen something between 20K and 40K, and also surprising myself at how good you can get with actually 10,000 acceleration as well. But this was with a 150 millimeter print size. And so my next thought was, well, what about 300, right? That's got to really show the differences here. And here I'm looking at 1000. Again, I'm pretty much stuck at 400 millimeters per second speed. But if I jump up to 2000, it's kind of surprising. At 400 millimeters a second, I'm getting more than halfway across that 300 distance. And in fact, it's the same for 500 as well. And I'm not doing so bad at 600 and 700 millimeters per second. When I look at 5,000, it's a huge jump across the board, and I'm doing really well at 800 millimeters per second. In fact, more than half that distance is being covered at 800 millimeters per second. 10,000, I see another substantial jump, and at this point, to be honest, it's just not suffering. And then after that, I find myself looking at these two charts, is anything over 40,000 worth it? In fact, is anything over 30,000 acceleration really worth it? And, I'm not sure. But again, looking at these, there is a sweet spot here. And I think that sweet spot is the 20,000 to 30,000 acceleration range. And truthfully, if you're at 10,000, you're not really suffering that much. So as far as the results are concerned, right, 48 volts provided the biggest jump in acceleration. It hit 50K acceleration at 550 millimeters per second. It almost hit the goal. In hindsight, may not have been a great goal. In addition, well, taking a look at this chart, again, you can see that anything above 30 wasn't really worth it, and 20K is looking awfully good, almost the same as 30. And again, you're probably not suffering too much at 10,000. Also at 48 volts, there's a very noticeable difference in how well the motors run. They really liked 48 volts. Now, 60 volts provided the largest acceleration increase overall. Um, and to be honest, I was kind of expecting that. um, but it also hit the 50K acceleration with the 600 millimeters per second, which was the actual goal. And it also had really nice running motors, or it had them running nicely. But in addition to acceleration, obviously it also provided the largest speed increase as well, because I was able to hit 1,000 millimeters per second at 60 volts. I might have been able to do it at 48 if I tried a little bit harder, but in my case, you can't lose with either 48 or 60 volts. So depending on your performance targets, what's nice about both of these is if you're not trying to hit 1,000 at 100,000 acceleration, you can actually lower the amperage of the motors at these higher voltages, which should actually keep your motors cooler running at these higher speeds. So even if you don't crank up the speed too much, there's a major advantage here in you can drop the amperage. So some warnings. These results were based on a 3D printer that was custom built by me. It has a very stiff X-rail, one that I'm strongly considering replacing because it doesn't seem to be breaking in. I've got an atypical combination of parts as well. I'm using 0.9 stepper motors. These tend to have less torque at higher speeds than 1.8 degree stepper motors. Also, I replaced the existing motors with high performance motors, the Krakens, and they're performing great. But if you went for Krakens with 1.8 or possibly kept your own, there's a chance you'd outperform some of what happened here because I'm using 0.9. Also, these motors are substantially more powerful than stock motors. You need to be careful. Make a mistake, smack something too hard with the motors, you may break something. Also, increased voltage means more hazard, so you need to be careful of the voltages and don't shock yourself. And most importantly, your results are almost guaranteed to be different than mine. If you increase the voltage, you'll get more performance, but don't expect the same results I did. Some other things to think about. You're going to need a second power supply to supply the additional power. You're going to have to find a place to put it, whether it be in, under, or besides the printer. You're probably going to need to change your MCU, or essentially the motor controller, to one that can handle the voltage. And again, one wrong electrical connection, meaning if you connect 60 volts to something that's expecting 24, you're probably going to fry those electronics. You're going to need to be comfortable installing the printer OS and maybe rewiring your printer. And again, high speed does not come with high quality print guarantee. You will need to resolve your resonance issues, because when you're trying to run at an acceleration of 1000, I guarantee you're going to have ringing and artifacts in your prints. And so you are going to have to do everything you can to make sure your printer can run at that rate safely and that Clipper can accommodate it. But anyway, for everything you've seen here, I've added links below in the description. And if you like what you see, please subscribe.